In 1925, Erwin Schrödinger discovered his law of silicon after learning about de Broglie's suggestion that matter can have wave-like properties. His goal was to predict the outcome of atomic equations. This equation is the differential equation whose solution is the wave function Trident x. Unfortunately, Schrödinger's equation can neither be derived nor proved. However, it can be proved to be plausible. De Broglie predicted the wave-like nature of matter. Now, there are some rules behind Schrödinger's equation. Not only can it not be solved without a potential energy function, but not all potential energy functions are acceptable. There also exist some boundary conditions for Schrödinger's equation. In order to solve Schrödinger's equation, you can use one of three methods: general techniques involving second-order differential equations, numerically, or just guessing. Basic physics uses the guessing method. The equation is so easy a caveman could do it, but for our example, we will use the human equivalent, Evan. The most basic method is guessing. To do so, use Trident x equals a Trident x plus b Trident x. If we can find the solutions to Trident x and Trident 2x by guessing, then the general equation is the solution to Schrödinger's equation. The rigid box model is described by a particle or wave in a solid box of length L experiencing perfectly elastic collisions. The basic questions we want to answer about quantum mechanics problems are: what are the allowed energies, what is the associated wave function, and where in the box is this particle found. The rigid box is a model and is not real. The dimensions of the box are x equals 0 and x equals L, and the particle moves freely with constant speed and kinetic energy between 0 and L. The particle will always turn at 0 and L regardless of kinetic energy. The potential energy is always 0 inside the box and is infinite outside of the box. The infinite potential energy is what we need to solve Schrödinger's equation. Due to the zero potential energy from 0 to L and the infinite potential energy outside of this range, the energy graphs will have very strict vertical boundaries. The oscillating wave function will be continuous, and at 0 and L the function equals 0. Here is Schrödinger's equation in a rigid box. The values defined by Schrödinger's equation in a rigid box are the only values of E which have physical meaning in Schrödinger's equation. We can determine the constant A by normalizing this equation. Therefore, here is the equation for a particle in the box.
For every particle in a rigid box, it must have energy, a wave function, and probability density for finding the particle at position x inside the box. In addition, a quantum particle in a box cannot be at rest, no matter how much the energy is reduced. If the particle were to be at rest, we would know both the velocity and the position, violating the Heisenberg uncertainty principle. As the quantum system number approaches infinity, the average behavior starts to mimic the classical solution. Niels Bohr's idea that the high quantum numbers in the classical world should blend into one is known as the correspondence principle. The rigid box is an infinite potential well, meaning that there is no chance that a particle could escape the infinity high wall. However, no box is infinitely strong, making the infinite potential well a more realistic model. The quantum mechanical solution has several important properties. First, the particle's energy must be quantized, meaning the particle in the potential well must be in one of the stationary states with quantum numbers n equals 1, 2, 3, and so on. Second, there are only a finite number of bound states because there are no stationary states with more energy than the potential energy of the well, because such a particle would not remain in the well. Third, wave functions are qualitatively similar to those of a particle in a rigid box, but the energies are somewhat lower. Lastly, wave functions extend into the classically forbidden regions. It is similar to a tennis ball, partially penetrating the racket strings before bouncing back without breaking the strings. The wave function oscillates until it reaches the classical turning point at x equals L, then decays exponentially within the classically forbidden region. Penetration distance into the classically forbidden region is n equals h bar over the square root of 2m times the quantity potential energy minus total energy. One example of quantum mechanics is the quantum well laser. A quantum well laser is created when a layer of gallium arsenide forms a potential well for electrons, with higher potential energy, gallium arsenide 1, forming walls on either side. As a result, electrons become trapped within the gallium arsenide layer. Surprisingly, everything in the layer only has one energy level. Another example of a potential well is the nucleus of an atom. A reasonable model for the nucleus is to think of the nucleus as a nuclear potential well created by the strong force. The strong force is what holds the nucleus together, even though all charges are positive, protons, or neutral, neutrons. Gamma ray emissions is one of the primary processes in the decay of radioactive elements. The protons ejected can have energies of millions of electron volts. Bound state waves are standing de Broglie waves. In addition to the boundary conditions, two other factors affect wave shape. First, the de Broglie wavelength is inversely dependent on the particle speed. A wave with a larger kinetic energy has a shorter wavelength, while a wave with a smaller kinetic energy has a longer wavelength. Second, a classical particle is more likely to be found where it moves more slowly. Probability of finding a particle also increases with the amplitude. When amplitude is larger, kinetic energy is smaller, and when amplitude is smaller, kinetic energy is larger. As a simple harmonic oscillator is f is equal to negative kx, a quantum harmonic oscillator is u of x is equal to 1/2 kx squared. Angular frequency is classically w is equal to the square root of k over m, but m's atomic model fails, so we need Schrodinger's equation. The wave functions are psi of x is equal to ae of negative x squared over 2b squared for the first energy level. Psi of 2x is equal to a of 2 x over b e negative x squared over 2b squared for the second energy level, and psi of 3 of x is equal to a3 times the quantity 1 minus 2x squared over b squared e negative x squared over 2b squared.
Energy levels go up at defined, evenly spaced intervals. Therefore, the wave functions of a quantum harmonic oscillator also go beyond the forbidden region. The probability of finding a particle increases as the particle moves away from the origin and slows down. Atoms are held together by spring-like molecular bonds. While the classical model for springs is acceptable for some purposes, it fails to explain some important features of molecular vibrations. Two atoms are connected by molecular bonds. If they are far apart, they are pulled together by polarization. If they are close together, they are pushed away by an electron repulsive force. However, there is a medium, R0, where the repulsive and polarization forces are the same. At this point, the two forces bring the particle to rest, but even at the lowest energy states, the particle will have energy and will vibrate. There is a certain point, U dissociate, at which the particles would have enough energy to separate and fly apart. However, most particles have nowhere near enough energy to do this. The energy associated with molecular vibration is quantized and can only have the values E vibration is about equal to n minus 1/2 h bar w, where n is equivalent to 1, 2, 3, etc. These levels are called the oscillatory function vibrational energy levels. Particles at room temperature are normally at energy level n equals 1. However, they can gain energy through absorbing photons of frequency f equals delta E over h. The levels of absorption are known for thousands of molecules and are often used to identify samples. A particle in a capacitor can be modeled as a particle trapped in a semiconductor. When the distance between plates becomes small enough, the particle's wave-like characteristics cannot be ignored. For example, as n increases, the space between each energy decreases. This opposite of the particle in the rigid box. In addition, the node increases as the wave goes right because the particle loses kinetic energy. Another characteristic is the probability of finding a particle is more likely on the right as the particle is moving slower. Finally, the electron penetrates beyond the classical turning point into the classically forbidden region. Covalent molecular bonds have a potential energy well related to their bond. The energy in the molecular bonds at n equals 1 shows a high probability that there is no node between the protons of H2+. If there is a node, the electron will not be found between the two protons. For the equation shown, when the energy calculated is less than 0, the wave function is called a bonding molecular orbital. Even when the protons repel each other, the electrons can hold them together. When the calculated energy is above zero, its wave function is called an antibonding molecular orbital. A molecular bond has an equilibrium length where the bond energy is minimum because of the interplay between the energies of the particles. The classical molecule cannot have a covalent bond because the electron would exist in the forbidden region. Quantum mechanical tunneling is when a particle decays exponentially through the classically forbidden region and emerges on the other side. During this process, there is no loss of energy and the wavelengths remain the same. Here is the probability equation for the probability that the tunneling will emerge through the energy barrier. The scanning tunneling microscope is one example of quantum mechanical tunneling. The microscope creates images by measuring the current through the tunnel created between the probe tip and the surface. A resonant tunneling diode is created when the energy level inside and outside a quantum well match, and there is a current through the device with the potential difference delta U resonant. The ability to drastically change current with just a small change in voltage makes the tunneling diode very useful in the digital circuits of high-speed computers. This concludes our video on one-dimensional quantum mechanics. We hope you enjoyed.